Hello dear students, this is Professor Anindo Das from Achievers and welcome to my lecture. In this lecture we will study the fundamental kinetic gas equation. At first we will deduce the gas equation and then we will discuss some important interpretations of that particular gas equation. So, in order to deduce the kinetic gas equation, we need to consider certain important assumptions. And what are those assumptions? Very simple, very simple. We'll consider the molecules to be, rigid hard spheres. We'll consider the molecules to be molecules of gas. They are considered to be rigid hard spheres. Okay? That means the molecules cannot be deformed or polarized. Okay? And we will also consider the collision between the wall of the container and the gas molecules to be elastic in nature. So, this collision is considered to be elastic in nature. Elastic in nature. We'll consider elastic collision. What does that mean? That implies conservation of both energy and momentum. Conservation of both energy and momentum. Conservation of both energy and momentum. Okay, so these are the fundamental considerations that must be taken under consideration for the deduction of this particular kinetic gas equation. Okay, very simple. Now, let us construct the shape of the container. Say we have a cuboidal container like this. I have got a cuboidal container like this. Okay. And let us mark the two walls like this. These two walls are to be considered. These two walls are to be considered. These two walls are to be considered. Now, let us consider this axis to be x-axis. And let us consider this wall to be the reference wall. Now you have got a molecule over here. You have got a gas molecule over here. Just we are considering a single gas molecule over here. You have numerous gas molecules inside the container, but we are considering a single gas molecule over here whose mass is m. Whose mass is considered to be m. And one more thing has to be considered. The distance between these two walls, the distance between these two walls is considered to be L. Okay. And the area of the reference wall, is considered to be A. The area of the reference wall is considered to be A. Okay. Now let us craft out a simplified 2D picture out of this. So a simplified 2D picture looks like this. The box looks like this. This is x-axis. These are the two walls. This one is the reference. And these two walls are separated by a distance L. And a molecule of mass m is moving inside this container. Say we are considering the motion only along x-axis. That is, the molecule is executing a to and fro motion in this direction. Okay, it is executing a to and fro motion in this direction. So we would now solely confine the motion of the gas molecules along x-axis. Okay, a to and fro motion like this. In this direction, it's plus u. The velocity is considered to be plus u in the positive x direction, and that along the negative x direction is considered to be minus u. Okay. Okay. So now when this molecule will collide with the reference wall, the initial momentum will be mass multiplied by velocity. This is the initial momentum. Of the molecule. This is the initial momentum of the molecule. Mass multiplied by velocity. And after collision, the molecule will revert back in the backward direction. The molecule will change its direction and it will move in the backward direction after collision. So it will revert back. So after collision, what will be the momentum? After collision, what will be the momentum? The magnitude of the velocity will remain all the same. Just what happens? The direction of the velocity will be changed. That means initially it was plus u, now the velocity will become minus u. There will be no change in the magnitude. Because there is no dissipation. The collisions are considered to be absolutely elastic in nature. That means there is no dissipation of energy. Okay, so what happens? It becomes minus mu after collision. Why? Because it's m multiplied by minus u. Mass is m, the mass doesn't vary, and the velocity becomes minus u. Initially it was plus u when it was moving in the positive x direction. Now it is reversing its direction and it is moving in the negative x direction. So the velocity becomes minus u. It remains invariant in magnitude. The magnitude remains all the same, just the sign is going to get reversed. So it's becoming minus u. And minus u multiplied by m becomes minus mu. So this is the final momentum. Okay. So what is the change in momentum of the molecule after collision? change in momentum of the molecule after collision. What is the change in momentum of the molecule after collision? The final momentum minus the initial momentum. The final momentum is minus mu, minus the initial momentum is mu. So it becomes minus 2 mu. As simple as that. As simple as that. Now, what is the time lag between two consecutive collision with the reference wall? What is the time lag between two consecutive collision with the reference wall? What is the time lag between two consecutive collisions with the reference wall? So, in order to execute collision with the reference wall just after a particular collision, so it has collided with the reference wall and then again it will collide with the reference wall. So what distance has it got to travel? After a collision with the reference wall, it has got to travel a distance L in this direction and it has to come back by a distance L so as to make another collision. So in order to make another collision, it has to travel a distance of 2L. So in order to make another collision with the reference wall, it has to travel a distance of 2L. So in order to execute another collision with the reference wall just after the collision made, the molecule has to travel a distance equal to 2L. At first it has to go in this direction, then it has to come back in this direction. So it needs to travel a distance of 2L. What time will it take? The speed is all the same, the speed is u. Velocity is either plus u or minus u. Velocity is plus u in this direction and minus u in this direction, but it doesn't affect the speed. The speed remains all the same, the speed is u. Because the speed is a scalar quantity. So if the speed is u and the distance is 2L, then the time lag between two consecutive collision will be distance divided by speed, that is time. So it becomes 2L by u. So you can say time lag between two consecutive collisions is equal to 2L by u. Okay. Okay. So just after the collision made, that is the trivial collision. This collision made is the trivial collision. That is not counted. Just after the trivial collision made, you are switching on the stopwatch. And you are waiting for the next collision. And the next collision is made at a time 2L by u. So basically time taken for a single collision is 12 by u, because the primary collision that was made, that is the trivial collision, that is out of count. You are not counting that collision. So just after that collision, you are putting the stopwatch on and you are waiting for the next collision. And the next collision is made at a time 12 by u. The next collision is made at a time 12 by u. So in 12 by u second, you'll find that one collision is made. That is, time taken for a single collision is 12 by u. Because it is the single collision made just after the trivial collision, and the trivial collision is not counted. So basically time taken for a single collision is 12 by u. So you can say in 12 by u seconds, so let us measure the time in second. In 12 by u second, number of collisions is equal to 1. Therefore, in 1 second, how many collisions will be made? Number of collisions will be u by 12. So you'll have u by 12 collisions. And for each such collision, change in momentum of the molecule, is equal to minus 2 mu. Change in momentum of the molecule is minus 2 mu. For each such collision, the change in momentum of the molecule is minus 2 mu. So for a single collision, the change in momentum is minus 2 mu, and you are making u by 12 number of collisions in 1 second. So in 1 second, what is the change in momentum? In 1 second, the change in momentum must be minus 2 mu multiplied by u by 12, because you are making u by 12 number of collisions in 1 second. For one collision, the change in momentum is minus 2 mu. So for u by 12 number of collisions, the change in momentum is naturally minus 2 mu multiplied by u by 12. And u by 12 number of collisions is made in 1 second. So naturally, in 1 second, the total change in momentum is going to be minus 2 mu multiplied by u by 12. So the change in momentum of the molecule in 1 second is equal to minus 2 mu multiplied by u by 12. This 2 is going to get cancelled out, and it becomes minus mu square by L. Now, students, what does this mean? The change in momentum of the molecule in 1 second. What does this mean? Let us get back to our secondary level, and let us recapitulate what we have studied in Newton's laws of motion. In Newton's second law of motion, we studied that the rate of change of momentum is nothing but the force. So this is nothing but the rate of change of momentum, the change in momentum in 1 second. So this is the force applied on the molecule. So this is the force applied on the molecule. The force applied on the molecule is minus mu square by L. The force that is applied on the molecule, is minus mu square by L. This is the force applied on the molecule. after collision with the wall. This is the force applied on the molecule. This is the force applied on the molecule after collision with the wall. This is the force applied on the molecule. Force applied on the molecule. So what will be the force applied on the wall? The force applied on the molecule is in this direction by the wall. So what is the force applied by the molecule on the wall? It is just the same but in the opposite direction. So this is the force applied by the molecule on the wall, and this is the force applied on the molecule by the wall. On the molecule by the wall. Force applied on the molecule by the wall. And what is the force applied on the wall by the molecule? The magnitude will remain all the same, just the sign will be reversed because it has got reversed in its direction. So the force applied on the molecule by the wall, it should be plus mu square by L. Just it will get reversed in the direction. So one can say, therefore, force applied on the wall by the molecule is equal to plus mu square by L. It's minus mu square by L, it will become plus mu square by L. This is the justification of Newton's third law of motion. Every action has got equal and opposite reaction. Every action has got equal and opposite reaction. So this is the force applied on the wall. Okay. As simple as that. So this is we have got the force applied on the wall. Now how can we calculate the pressure on the wall? The pressure on the wall is nothing but the pressure of the gas that we already know. So how can we calculate the pressure? We know that pressure is nothing but force per unit area, and we have considered the area to be A. So what is the pressure applied on the wall? Force divided by area. What is the value of the force? The value of the force is mu square by L. So you need to divide mu square by L by the area. So you can say pressure on the wall is equal to, what should be the pressure? Pressure on the wall is equal to mu square by L divided by area. We will simply write pressure on the wall as P. We will simply write the pressure on the wall as P. And we all know that length into area is nothing but the volume of the container V. So from here one can write P equal to mu square by V. As simple as that. So pressure on the wall becomes mu square by V. This is for a single molecule. So I have got the data for a single molecule. We have got the data for a single molecule. A single molecule is going to apply this amount of pressure on the wall. A single molecule is going to apply this amount of pressure on the wall. So one can say the pressure applied by a single molecule moving along x-axis is given by P of what? Of that single molecule. Let us represent that single molecule by I. So pressure applied by the single molecule I when it is moving only along x direction is equal to mu square by v. We'll represent it in this way. This is more explicit representation. This is more explicit representation. Pressure applied by the ith molecule, which is constrained to move only along x-axis, is going to be equal to mu square divided by the volume V of the container. Now suppose the container is comprised of a molecular set J containing 1, 2, 3 up to n number of molecules. I is a random variable. This is the set J. This is the set of molecules. This set J basically represents the molecular set, and say there are n number of molecules, and say the velocity of the first molecule is u1 along x-axis, that of the second molecule is u2, that of the third molecule is u3, ith molecule is ui, nth molecule is un. Okay. So what should be the total pressure? What should be the total pressure along x-axis? What should be the total pressure along x-axis? So therefore, total pressure along x-axis. What should be the value of the total pressure along x-axis? Is equal to summation over Pix, where I runs from 1 to n. Okay. Okay. As simple as that. So it becomes, see, m by v is a constant. So it moves out of the summation series. And within the summation series, you'll have just this factor ui. So within the summation series, you'll have this factor ui square, where I runs from 1 to n. Okay. Okay. So pressure along x-axis, this is given by this particular form. This particular form. Okay. So therefore pressure, let me correct it. Therefore total pressure acting along x-axis is given by summation over I equal to 1 to n Pix equal to m by v summation over I equal to 1 to n ui square. Okay. So I think you all have understood this part. Okay. Now we'll come back to this calculation in a moment. At first, let us have a look into the matter. We need to clarify some important things over here. See, we have considered this wall to be the reference wall. We have considered this wall to be the reference wall. This wall has been considered to be the reference wall. And what is the definition of pressure? The definition of pressure is the force applied on the reference wall per unit area in a direction perpendicular to the reference wall. So it's acted in a direction perpendicular to the reference wall. So for that purpose, if we are considering the reference wall along YZ plane and this to be the x-axis, then we all know that x-axis is perpendicular to the YZ plane. So the pressure that is acting along x-axis is nothing but the total pressure. So the pressure acting along x-axis is nothing but the total pressure in context to this reference wall. Because by definition we know that the pressure is nothing but force acting on the reference wall per unit area of the reference wall in a direction perpendicular to the wall. That means you need to consider the direction perpendicular to the wall. And if you are considering the reference wall along YZ plane, then the direction perpendicular to the reference wall is nothing but the x-axis. So basically what is the need of the hour? The need of the hour is to simplify things. The total pressure acting along x-axis, this is nothing but the total pressure. This is nothing but the total pressure. This is nothing but the total pressure. In context, the total pressure in context to the reference wall. The total pressure in context to the reference wall. This is the total pressure in context to the reference wall. So one will write simply P equal to m by v multiplied by summation over I equal to 1 to n Ey square. Okay. This P is the total pressure. This P is the total pressure. So far so good. We have understood things. We have applied simple physics and we have understood this thing. So we have got, let us bring this equation forward, P equal to m by v multiplied by summation over I equal to 1 to n Ey square. Now, we define mean square speed as angular bracket u square. It is the mean of the square of speed. That means you have to add up the squares of speed and you have to divide by the number of terms. The number of terms is capital N because you have capital N number of molecules. So you have 1 by capital N multiplied by sum of the squares. So it is nothing but This. And you have one more term. The term is root mean square speed. It is written as URMS. Is nothing but square root of mean square speed. So it is nothing but square root of 1 by n summation over ui square. So we'll write stuff in terms of URMS. That is the convention. So one can write it like this. Therefore, u square average is nothing but URMS square. You just square both sides. So you'll get this. Put the limits, I equal to 1 to n, I equal to 1 to n. Okay. ui square. Therefore, from here one can write summation over I equal to 1 to n ui square is nothing but n multiplied by URMS square. So you replace this term by this one, summation over ui square. So naturally, the expression of P becomes P equal to m by v multiplied by n URMS square. As simple as that. As simple as that. As simple as that. Okay. Now, if we draw the vector model, then if this be the z-axis, this is the x-axis, and this is the y-axis, this is basically the direction of the velocity c. So we'll have the component of c along x-axis. The component of c along x-axis is u. The component of c along y-axis is v, and that along z-axis is w. So if you drop the components, one on the xy plane and another on the z-axis, then this is the component along the z-axis, this is w. This is the component along the y-axis, this is v, and this is the component along the x-axis, this is u. This is the simple way of splitting the components. We all know these things. So, one can write C as ui vj plus wk. And c square is nothing but c dot c. It's u square plus v square plus w square. Therefore, if you take c square average, then it's u square average plus v square average plus w square average. Very simple vector equations. We are already acquainted with these things. Now students, you have to visualize one important thing. The molecules are supposed to move in an unbiased manner. What does that mean? That means the probability of motion along x-axis is exactly equal to the probability of motion along y-axis, is exactly equal to the probability of motion along the z-axis. The probability of motion along x-axis, the probability of motion along y-axis, and the probability of motion along z-axis, all these are same. They are all the same. It can't be so that in x-axis it will move in a greater probability, in y-axis it will move in a smaller probability, in z-axis it will move in another probability. It cannot happen so. Because the space is equally accessible by the molecule. So the molecule can move in all the directions with equal probability. That means the motion is unbiased. And this unbiased motion will render all these quantities to be equal. So this unbiased symmetry, the unbiased symmetry in molecular motion will render these quantities to be equal. So the unbiased symmetric molecular motion will basically render all these three quantities to be equal. Render all these three quantities to be equal. And if they are equal, then obviously each of them will be equal to 1/3 c square average. 1/3 c square average. Because sum of these three is equal to c square average, and if all of these three quantities are equal, then obviously they will be 1/3 of c square average. And by similar logic, if u square average is u RMS square, then c square average is c RMS square. So this is nothing but 1/3 c RMS square. We'll define in an analogous manner, just we'll replace u by c. That's all. So in place of u square average, we will substitute 1/3 c RMS square. So here, in place of u RMS square is u square average. In place of that, we will substitute 1/3 c RMS square. Okay. So if you do so, what will we get? We already have got P equal to m by v n. Then we have got 1/3 c RMS square. U RMS square is replaced by 1/3 c RMS square. So from here, we can deduce the famous kinetic gas equation, PV equal to 1/3 mn c RMS square. This is the famous kinetic gas equation. This is the famous kinetic gas equation. This is the famous kinetic gas equation. Okay. So we have understood the deduction of this famous kinetic gas equation. Now we will see some implications of this famous kinetic gas equation. So let's move on to that. Let's move on to that. So for that purpose, let's move on to that in a moment. At first, we will try to get one important expression of CRMS. So this is the expression already known to us, PV equal to 1/3 CRMS square. And we also know that this is the kinetic gas equation. And we also know that PV is equal to nRT. Okay. So we have got PV to be equal to 1/3 Mn CRMS square, which is equal to nRT. Now students, if we look into this is mass per molecule, this is number of molecules. Number of molecules means number of moles multiplied by Avogadro number. So if we do that, then it becomes 1/3 M N Avogadro CRMS square, that is equal to nRT. So what next? What's next? You just cancel this to n. Then the expression of CRMS will become square root of 3RT divided by M into Avogadro number. You can write it in two different ways. Either you replace this R by Avogadro number as Boltzmann constant Kb, and you write it in this way, root over of 3 kBt by m. Or what you can do, you can replace mass of molecule multiplied by Avogadro number by molar mass capital M. You can also do that. And you can write the result as root over of 3 RT by capital M. Both the expressions are correct. So this is the expression of CRMS, that's what we have got. Done. Done. Now, students, let us move on to the expressions of the energies. The expressions of the energies. So let us represent the energy per molecule as epsilon k bar. K stands for kinetic energy. All the molecular energy is kinetic, nothing potential. So we are putting a k over there. So epsilon k bar is the molecular kinetic energy. E k bar is the molar kinetic energy. And E is the total energy. That too is kinetic in nature because you don't have any potential energy over here. So how can we calculate epsilon k bar? Kinetic energy is nothing but half into mass into speed square. So half m CRMS square. As simple as that. And what is CRMS? CRMS is root 3 kBt by m. So just do one important thing. Half into m into, just take the square of this square root. So the square root will get cancelled out. It will get 3 kBt by m. M will get cancelled out. So it becomes 3 by 2 kBt. Done. Done. Now Ek average. Ek bar. Sorry, Ek bar. Not average. Is the molar kinetic energy. You have to do nothing. This is molecular kinetic energy. Just multiply the molecular kinetic energy by Avogadro number. So Avogadro number multiplied by molecular kinetic energy. That will yield the molar kinetic energy. So it's Avogadro number multiplied by the molecular kinetic energy. And we all know that if we multiply this Avogadro number by Kb, if we multiply this Avogadro number by Kb, it will become R. So this becomes 3 by 2 RT. Done. One can write RT as PV bar. Why? We all know that PV is equal to nRT. So RT is equal to P into V by N. V by N is nothing but molar volume V bar. So one can replace this RT by PV bar. That one can always do. But the fundamental expression is 3 by 2 RT. So I've got it. So I've got the molar kinetic energy. Now you need to calculate the total kinetic energy. The total kinetic energy is very simple. You have got the molar kinetic energy, so just you need to multiply. You need to multiply this molar kinetic energy by number of moles. So 3 by 2 RT multiplied by number of moles, so it becomes 3 by 2 nRT. It's 3 by 2 nRT. nRT is nothing but PV, so it's 3 by 2 PV. It's 3 by 2 nRT or 3 by 2 PV. Done. Done. As simple as that. Very simple. Now you have to evaluate the expression of density. You have to evaluate the expression of density. So how can we do that? We all know that PV is equal to nRT. V is mass, total mass of the gas. Let us write that by m dash. Because mass per molecule is written as m, so we are writing the total mass as m dash. So volume is mass by density of the gas, d, is equal to nRT. So the expression of d will become p m dash by nRT. Okay. Now m dash means total mass. Total mass means number of moles multiplied by molar mass. Total mass is nothing but number of moles multiplied by molar mass. So Nn will get cancelled out and it becomes P into molar mass by RT. We all know this equation. P into molar mass by RT. You can also write this expression in terms of CRMS. Because we know that from this expression, CRMS square, if you square both sides, CRMS square and use this equation, CRMS square is 3 RT by M. So M by RT is 3 by CRMS square. So you replace this M by RT by 3 by CRMS square. So the expression, the total expression of density becomes D equal to P into molar mass by RT. One can also write it in this way, 3P, P remains as it is, 3P divided by CRMS square. So from here also one can write that CRMS is proportional to root over of P by D. CRMS is equal to basically root over of 3P by D. So CRMS is proportional to root over of P by D. CRMS is proportional to root over of P by D. One can write it in that way also. Okay. Okay. As simple as that. Now, we have some applications of the kinetic gas equation. We have got widespread applications of this kinetic gas equation, PV equal to 1/3 mn CRMS square. We can justify all the ideal gas laws using this kinetic gas equation. So let us start with the Boyle's law. Let us start with the Boyle's law. Let's start with the Boyle's law. See, we have to modulate the equation. We already know PV equal to 1/3 mn CRMS square. Okay. And we have adjusted this equation in this way. We have broken this equation into two terms. 2/3 capital N multiplied by half m CRMS square. If these two cancels out, we will again yield this equation. So these two are same, all the same. This 1/3 m CRMS square is nothing but 1/3 m CRMS square is nothing but epsilon k bar. We have already defined epsilon k bar. It is the molecular kinetic energy. So you can write it in this way. So basically, you have got PV to be equal to 2/3 n epsilon k bar. I think you all have understood this one. Just the trick is over here. You have to split this term into two meaningful parts. Okay. And you are getting this. And what we have got for epsilon k bar, what is the expression of epsilon k bar? It's 3/2 kBT. We have already found that. That means this epsilon k bar is a function of temperature only. So it's a function of temperature only. So epsilon k is only dependent on temperature. It's a function of temperature only. So one can say that if T is constant, epsilon k is constant. Epsilon k is only a function of temperature. So if you keep temperature constant, epsilon k bar will remain constant. If epsilon k bar remains constant, so this part is constant. So if T is constant, this part is constant. If mass of the total mass of the gas is constant, if m dash is constant, then n is also constant. Total mass is proportional to the number of molecules. If you keep the total mass to be constant, then the number of molecules, number of moles, everything will remain constant. So this n is also constant. That makes RHS constant, right hand side constant. So what happens? You are going into the conditions of Boyle's law. In Boyle's law, you have taken an ideal gas. You have kept temperature constant. Keeping temperature constant means epsilon k is held constant. Epsilon k bar is held constant. Then you are keeping mass constant. Keeping mass constant means you are keeping the total number of molecules to be constant. So these two are constants. 2/3 is already a constant. So right hand side becomes constant. That makes PV constant. And that is nothing but Boyle's law. P1 V1 equal to P2 V2 equal to P3 V3. And so on and so on and so on. So in this guise, we have basically justified the Boyle's law out of the kinetic gas equation. So this was our first application. Now students, let us move on to the second application. The second application is Avogadro's law. How can we do that? Let's see. Again, we are ending up into the same equation. PV is equal to 2/3 n epsilon k bar. We are ending up into the same equation. Now, in Avogadro's law, we keep temperature and pressure constant. So, if we keep temperature and pressure constant, then what happens? If this is constant, if temperature is constant, that means epsilon k bar is also constant. So, you have got this term to be a constant. This pressure is constant. This 2 by 3 is constant. So, V is directly proportional to N. V is directly proportional to N. Now, do you remember Avogadro's law? What does it state? It states that at constant temperature and pressure, equal volumes of all ideal gases will contain same number of molecules. Equal volumes of all gases will contain same number of molecules. Equal volumes of all gases will contain same number of molecules. So that means volume is directly proportional to the number of molecules. That's it. That's it. Very easy. Very easy. So you have proved that. Next. Let's move on to the Dalton's law. In Dalton's law, we know that the total pressure is basically the sum of the partial pressures. The total pressure is basically the sum of the partial pressures, and that is to be established out of the kinetic gas equation. And you have got a set of gas molecules. The set is given by J, 1, 2, 3 up to N. So, we will start with the basic kinetic gas equation. We know that PV is equal to 2/3 N epsilon k bar. Now, what is epsilon k bar? It is nothing but the molecular kinetic energy per molecule. Now, if you multiply kinetic energy per molecule by total number of molecules, you will get the total kinetic energy. So, this is the total energy. Energy per molecule multiplied by total number of molecules is the total energy. So, total energy is becoming 3/2 PV. So, I have used this equation. Now, students, energy is a scalar quantity. So, you can just add up all the energies. So, the total energy is basically sum of energies of each of the gas molecules. That means E1 plus E2 plus E3 plus EI and so on. So, total energy can be expressed as E1, let us write it in this way. Total energy can be expressed as summation over EI. In Dalton's law, which factor is kept constant? The volume of the container is kept constant. So you have to do nothing with the volume of the container. The volume of the container is kept constant. I think all remember. The volume of the container is kept constant because you are taking a single molecule hypothetically into a replica of the original container of the same volume. So volume is constant. So basically, EI is written as PVI 3 PVI by 2. E is 3 PV by 2. So it becomes PIV by 2. V is constant. 3 PIV by 2. 3 PIV by 2. It will not vary V. If it is EI, For the ith term, 3 by 2 V is constant. Only the pressure will become Pi. So, E is becoming equal to 3 by 2 PV, which is equal to summation over, you see, you are putting this term over here. Now 3 by 2 V is a constant, so it will be pulled out of the summation, and you will just have Pi into the within the summation series. E is already equal to 3 by 2 PV. We have already established that. And now you are putting E equal to summation over EI, and you are substituting the value of EI, 3 Pi V by 2. Now 3 V by 2 is a constant, so that is pulled out, and you are getting this. So you see 3 V by 2 is getting cancelled out, and thereby you are getting P equal to summation over Pi. That means total pressure is sum of the partial pressures. So I have established the equation. Very easily you have established this equation. Okay. Now students, let us move on to the Graham's law of effusion. In Graham's law of effusion, we know that at constant temperature and pressure, the rate of effusion is directly proportional to 1 by square root of density. Now, basically, if we apply the logic, then the rate of diffusion is directly proportional to CRMS. Greater is the speed, greater will be the rate of effusion. Greater is the speed, greater will be the rate of effusion. And we have also shown that CRMS is proportional to P by D, square root of P by D. Now if you keep temperature, pressure constant, then this P is constant, then CRMS becomes proportional to square root of 1 by D. So R is already proportional to CRMS, and CRMS under this constant is proportional to 1 by square root of D. So if we connect these two, we are getting R to be proportional to 1 by square root of density. Very easy. Very easily sorted. Very easily sorted. Isn't it? Now, let's move on to some exemplar problems. Let's check. When temperature of an ideal gas is increased from 27 to 927 degrees centigrade, the kinetic energy will be? What will happen to the kinetic energy? The kinetic energy, total kinetic energy is basically equal to 3 by 2 nRT. Have proved that. So E is directly proportional to T. So one can write E2 by E1 equal to T2 by T1. Here T2 is 927 degrees centigrade. Means 1200 Kelvin, you have to convert it into Kelvin. And 27 degrees centigrade is 300 Kelvin. 4 times. So E2 will become 4 multiplied by EI. So this will become 4 times. Very simple problem. Very simple problem. Okay, let's move on to the next. You have got two flux, X and Y, having capacity 1 liter and 2 liter. So I have got two flasks. One is flask X, another is flask Y. Flask X has got capacity 1 liter and flask Y has got capacity 2 liters. And each of them contains 1 mole. So this contains 1 mole, this also contains 1 mole of a particular gas. The gas is same. The temperature of the flasks are so adjusted that the average speed of the gas molecules in X, the average speed of the gas molecules in X is twice as those in Y. So if the temperature is Tx over here and the temperature is Ty over here, then what they're saying? They're saying that the temperature is so adjusted, the temperature of the flasks are so adjusted that the average speed of the molecules in X is twice as those in Y. That means average speed of the molecules in X, C average, which is proportional to square root of T. Are talking of this. So let's write it in a different manner. Basically, average speed or root mean square speed, everything is proportional to square root of temperature. You already know that. And they have given Cx by Cy to be equal to 2. And that is equal to root over of Tx by Ty. So from here, you are getting Tx by Ty to be equal to 4. So pressure in flask X would be, what would be the pressure? What would be the pressure? It's very simple. Here I've got same number of moles, so Px Vx by Tx equal to Py Vy by Ty. We'll apply this. As the number of moles is same, you can always apply this. Now Px by Py should be equal to Vy by Vx multiplied by Tx by Ty. Vy by Vx multiplied by Tx by Ty. What is Vy by Vx? 2 liter by 1 liter, this is 2. What is Tx by Ty? That is 4. So 2 multiplied by 4 is 8. So that will be 8 times of Y. As simple as that. As simple as that. Let's move on to the final problem. The root mean square speed of the molecules of a diatomic molecule is U. So I've got a diatomic molecule, say X2. Its CRMS is given to be equal to U. This is equal to basically square root of 3R T of the diatomic molecule divided by molar mass of the diatomic molecule. Now what you have done, You have doubled the temperature. You have doubled the temperature. You have doubled the temperature. What happens? The molecules dissociate into two atoms. The molecules, what happens? The molecules dissociate into two atoms. Obviously, now the molar mass of X is half of mx2. It dissociates into two atoms. What should be the new CRMS? Let the new CRMS be CRMS dash. That is equal to root over of 3R. Now the temperature is 2 into Tx2. So 2 Tx2 divided by mx. mx is half mx2. So put half mx2 over here. So it becomes 3 multiplied by 4 RTx2 divided by mx2. So you can write it in this way. If this 4 gets out of the root, it becomes 2 multiplied by root over of 3 RTx2 divided by mx2. Root over 3 RTx2 by mx2 is nothing but CRMS. The original CRMS. So this is 2 multiplied by original CRMS. So the new CRMS is twice the original CRMS. And the new CRMS was U. So it's nothing but 2U. So answer is 2U. Okay. It's very simple. So that's all, students, for today's class. Bye bye for now. Jai Hind, Vande Mataram.